Hello AUTOML and welcome to this presentation of our work QDOES Population-Based Quality Diversity Optimization for Post-Hoc Ensemble Selection in AUTOML. Our work tries to improve the performance for a typical machine learning problem with tabular data. That is, assume we are given a data and a goal, like data about patients, and we want to predict how a patient reacts to a new drug. Then, generally and simplified speaking, our goal is to produce a model that allows us to predict the reaction of new patients. And to do so, we first must build a model. Therefore, we typically train and evaluate many models and then pick the best found model, which may already be an ensemble like random forest. AUTOML then usually automates such a process among many other things. The process of post-hoc assembling now builds upon this framework in AUTOML. Instead of picking the best model, we first select a subset of all evaluated models and then build an ensemble post-hoc which we return as the final model. We define all of these steps to be part of post-hoc assembling. For this work now, we are interested in specifically post-hoc ensemble selection, which is a specific type of post-hoc assembling. In detail, while building the ensemble, post-hoc ensemble selection focuses on creating a final ensemble that only uses a subset of all selected models, making the ensemble small and thus the final model more efficient in terms of inference time. To solve this problem, greedy ensemble selection by Caruana et al. Has been used in AUTOML. Greedy ensemble selection searches in a greedy manner for an optimal weight vector to aggregate the predictions of base models. It performs ensemble selection as the final weight vector is sparse and only uses a subset of all base models for the final ensemble. Yet greedy ensemble selection is only a simple deterministic greedy search. And still it is frequently used by AUTOML systems like AutoGluon, AutoEscalon, AutoPytorch or MLJAR supervised. As we expect a deterministic greedy search to be suboptimal for AUTOML, we asked ourselves if we can do better and were motivated to improve upon greedy ensemble selection. As a solution, we propose to introduce populations and randomness to ensemble selection for AUTOML, following their success in other optimization settings. Based on this, we created two methods. First, quality optimization for ensemble selection, and second, building upon the previous idea, quality diversity optimization for ensemble selection. For more details on these methods, let me share their concepts. In detail, we propose quality optimization for ensemble selection, which performs an evolutionary search using mutation and crossover operators while maintaining a population of best performing ensembles. Furthermore, it performs ensemble selection as the population, mutation, and crossover follow concepts from greedy ensemble selection, resulting in sparse weight vectors. The intuition is as follows. We start with a population of random initial ensembles, then we randomly create new ensembles with mutation and or crossover, and afterwards we keep only the fittest ensembles. And then we simply loop this process for a specific number of iterations. The novel part of our work are the initialization, mutation, and crossover operators, which we designed such that we obtain sparse weight vectors in the end, similar to greedy ensemble selection. Moreover, we built upon quality optimization for ensemble selection with our second method. We introduce quality diversity optimization for ensemble selection, which builds upon QoES but maintains a population of best performing, differently behavioral diverse ensembles during optimization. Specifically, it leverages the concept from the domain of quality diversity optimization and ensemble diversity. The intuition is that we perform the same evolutionary search as for QoES, but we change the way we maintain the population. Following the ideas from the domain of quality diversity optimization, we first split the population into grid cells based on the behavior of the ensembles. In our case, the behavior of ensembles is equal to the diversity of ensembles. Here, diversity is understood as a measure of the degree to which models in an ensemble make different errors. Then, instead of taking the fittest ensemble, we take the fittest ensemble per grid cell, fostering diversity of ensembles while optimizing for quality with the intention to boost performance. Next, let's talk about some details. To start, how do we measure ensemble diversity to create the grid cells? In our implementation, we used a combination of two measures. First, a measure following previous work named average loss correlation, which measures the average correlation between loss vectors over all pairs of models in an ensemble. Second, we propose a novel method unique to AUTOML or cache-based solutions called configuration space similarity, which measures the average pairwise similarity of configurations using the Gauss similarity. Their combination then allows us to define a grid cell which we use for quality diversity optimization. Next, we introduce randomness during optimization. For example, we can randomly initialize a population of ensembles. Furthermore, for sampling, we propose to use either deterministic sampling, tournament selection, or dynamic sampling. Dynamic sampling is an adaptive approach that either performs random or deterministic sampling based on a ratio that is adapted during optimization. Crossover, we perform 2-point or average crossover on the sampled members of the population while guaranteeing that the results weight vectors stay sparse. Additionally, we decide randomly if we use crossover or not. The likelihood for this is adapted throughout the run. And lastly, for mutation, we follow the idea of greedy ensemble selection, but randomly select a new or repeated ensemble member. This guarantees that mutation keeps the resulting weight vector sparse. Furthermore, we also randomly decide whether we mutate or not with an adaptive likelihood. Lastly, we explored pruning strategies for ensemble selection. That is, how we select the models in the first step of post-hoc assembling. We looked at two methods: TopN, following AUTOScalen's default, which prunes to the n best models based on the validation score, and a second method called SiloTopN, following AUTOGluon's default, which prunes to n models such that many top-performing models of each algorithm family, in other words Silo, are kept. With that, we look at the results. To start, let me explain the experimental setup. We performed all our experiments for two metrics, balance accuracy and ROC AUC. In other words, we had to run everything twice, as these represent different optimization tasks for the AUTOML system and post-hoc assembling. Moreover, we performed our experiments on 71 datasets for classification with 10-fold cross-validation from the AUTOML benchmark. We obtained data to compare post-hoc assembling methods, that is, trained and evaluated models, by running AUTOScaler1. We ran AUTOScaler for 4 hours on 8 CPUs for each fold for each metric. Afterwards, once we had the data for post-hoc assembling, we compared greedy ensemble selection and our proposed methods. Therefore, we exhaustively evaluated a grid of 216 configurations for our proposed methods using leave one out cross-validation. Here we show the critical difference plots for test scores. The axis at the top shows you the mean rank, lower is better, and methods connected by a bar are not statistically significantly different. Here, single best refers to the best model seen during validation, or in other words, no post-hoc assembling. Here we observe for ROC AUC that assembling is significantly better than no post-hoc assembling, and that QoAS and QoDoAS outrank greedy ensemble selection, but not statistically significantly. For balance accuracy, we observe the same, but we also see that we fail to beat greedy ensemble selection for multiclass. Next, let's look at relative performance. Here we use normalized improvement, whereby -1 represents the performance of the single best, that is no assembling, and 0 the performance of the best model on a dataset. Moreover, we see the outliers with a normalized improvement lower than -2 in the brackets next to the method's names. We observe that QoAS generally performs well, as indicated by the highest median, the horizontal bar in the box plots, but as seen, fails to perform better than greedy ensemble selection for balance accuracy and multiclass. Yet, as it turns out, this and the results in general are heavily influenced by overfitting. If you look at the validation score, we see a large rank switch and statistically significance across the boards for our methods. Moreover, we observe that diversity during optimization helps in this case, while it does not generalize to testing data. In terms of efficiency, we observe that the resulting weight vectors for QoAS and QoDoAS are also sparse. As you can see here, the ensemble size is not much larger than for greedy ensemble selection. Moreover, especially considering that the methods selected from 50 models in total. Finally, we looked at the hyperparameters. We found that the pruning strategy was the most important hyperparameter, and SiloTopN was always more influential than TopN. Moreover, we found that random initialization was more robust and regularly better than deterministic initialization, which is quite interesting, as greedy ensemble selection by design cannot start with a random initialization. To recap our results, we found that post-hoc ensemble selection always performs better than no assembling. Moreover, our proposed methods outrank greedy ensemble selection, but only significantly on validation data. And finally, we found that overfitting is a serious challenge for post-hoc assembling in AUTOML. For more details, see our paper or talk to us at the conference. Thank you very much.